Supernovas are not just spectacular cosmic events, they are essential phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space, from which new stars, planets, and even life itself are formed. In essence, supernovas serve as both destroyers and creators of galaxies. In the study of supernovas, imagery plays a crucial role in understanding these immense explosions. Over the years, advances in imaging technology have allowed astronomers to capture stunning views of supernovas at various stages, revealing intricate details of their structure and the elements they expel into space. One prominent example is the story of Betelgeuse, a red supergiant star. Images have helped scientists understand its behavior, especially as it has recently attracted attention due to its sudden dimming and brightening. This variability sparked widespread interest, leading to speculation that Betelgeuse might be on the verge of a supernova explosion. A dust cloud surrounding Betelgeuse, observed through telescopes and captured in images, was initially thought to be a precursor to this explosion. However, it later became regarded as a natural phenomenon in the life cycle of red supergiants. But why did scientists initially think this star might be the next observed supernova? Betelgeuse, perched on the shoulder of the Orion constellation and visible to the naked eye, holds a prominent place in the sky. Let's explore Betelgeuse's life cycle, an intriguing journey from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began as a massive star, burning hydrogen in its core, like many others. However, due to its large mass, it evolved rapidly, undergoing successive phases of nuclear fusion. Its significant mass set it on a different evolutionary path than smaller stars like our Sun. While the Sun is currently a stable, main-sequence star, slowly converting hydrogen into helium, Betelgeuse's larger mass caused it to deplete its hydrogen reserves quickly, evolving into a red supergiant. The key difference between Betelgeuse and the Sun is their mass. Betelgeuse, with about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. This intense fusion causes Betelgeuse to burn its fuel rapidly, leading to an unstable structure and significant fluctuations in brightness. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a longer, more stable hydrogen-burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning heavier elements than hydrogen. The internal pressure caused the star to swell, transforming it from a main-sequence star into a red supergiant, marked by its enormous size and brightness variability. The star expands and contracts as it undergoes complex nuclear processes. Recent observations suggest that Betelgeuse might be nearing a supernova. Its dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be entering the final stage of its life. These brightness changes are thought to be related to internal processes, possibly signaling the beginning of core collapse. Scientists have analyzed Betelgeuse's pulsations, which follow cycles of 185, 230, 420, and 2,200 days, to better understand its internal dynamics. The longest cycle, 2,200 days, is particularly intriguing, as it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion, a stage that precedes a supernova explosion. But what are the complex nuclear processes that ultimately determine when a star's life must come to an end? In the core of a massive star like Betelgeuse, nuclear fusion transforms hydrogen into helium, releasing enormous amounts of energy. As the star ages, heavier elements begin to fuse, forming layers, much like the layers of an onion. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to a gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core succumbs to immense gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core briefly inflates before exploding, creating a shock wave that tears the star apart. A supernova explosion releases an extraordinary amount of energy, briefly outshining an entire galaxy. The mechanics of this process involve a complex interplay of nuclear collapse, gravitational forces, and intense heating. The shock wave from the collapsed core moves outward, ejecting the star's outer layers into space. Ancient astronomers recorded these bright phenomena for thousands of years, often describing them as guest stars or new stars. The earliest recorded observation of a supernova dates back to 185 AD when Chinese astronomers saw a guest star visible for 8 months. Though rare, astronomers still study supernovas today, especially when they lead to unusual phenomena like gamma-ray bursts. Gamma-ray bursts, GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merging of neutron stars. These bursts are among the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit over its entire 10 billion-year lifetime. One of the most significant GRB events occurred in October 2022 with the detection of the brightest gamma-ray burst ever recorded, known as the Boat GRB, brightest of all time. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy approximately 2.4 billion light-years away. This event was notable not only for its brightness but also for its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it impacted Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of a massive star's core can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are usually followed by a supernova explosion. The Boat GRB was remarkable not only for its brightness but also for providing insights into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might reveal the origin of elements heavier than iron, which are typically formed in supernovae or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and highlighting the mysterious nature of these cosmic phenomena. To determine the cause of the flare, scientists employed various observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially made it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months for the brightness to fade enough to allow for detailed observations. Eventually, a relatively faint supernova remnant was detected, which was surprising given the intensity of the gamma-ray burst. The Boat GRB also provided insight into the nature of gamma-ray bursts. The exceptional brightness and long duration of this event suggested that the GRB was highly focused, with narrow jets of energy directed straight toward Earth. This narrow focus likely contributed to the observed intensity, as GRBs are generally directional phenomena. The narrow jets were likely the result of a rapidly rotating star with a strong magnetic field. Producing a powerful and concentrated flare was probably the result of a rapidly rotating star with a strong magnetic field. While the Boat GRB, brightest of all time, has provided valuable insights into gamma-ray bursts and supernovae, scientists continue to seek answers to the mystery surrounding Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimming and brightening are part of its natural behavior as a variable star. Unlike our Sun, Betelgeuse is an extremely explosive, low-density plasma cloud that frequently changes shape. Simulations created by scientists illustrate Betelgeuse's behavior, with cycles of brightness and dimness occurring every 400 days, and a longer cycle of about 2,000 days. Recent studies have attempted to explain the Great Dimming event that occurred in 2020. Observations from various telescopes over the past 15 years have provided significant insights. Using various frequencies, including microwaves and infrared, scientists were able to penetrate Betelgeuse's layers and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculations that Betelgeuse was about to explode. Instead, internal activity within the star seems to have caused material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from Earth's view. Further study of Betelgeuse's behavior revealed that the star experienced two shock waves, one in 2018 and another a year later. These shock waves disrupted the surface, creating hot and cold spots, as confirmed by ultraviolet imaging from the Hubble Space Telescope. These shock waves and their aftermath disprove the earlier assumption that Betelgeuse was on the verge of becoming a supernova, instead showing that these behaviors are part of the star's natural life cycle. Betelgeuse is also characterized by its rapid rotation rate, unlike typical red supergiants, which rotate slowly. Betelgeuse rotates at about 3 meters per second, which initially led researchers to believe it might have once been part of a binary star system that collided. However, recent research suggests that its rotational speed may be influenced by fast-moving convective cells within the star, contradicting earlier assumptions about its rotational behavior. Despite this unusual behavior, the research suggests that Betelgeuse is unlikely to explode as a supernova during our lifetime. It is currently more akin to a variable red supergiant nearing the end of its life, but not yet approaching a supernova explosion. This leads to a question that concerns many: how would such an explosion affect our planet? While a supernova is not expected to pose an immediate threat, the explosion of a star within a few light-years of Earth could have an impact on our atmosphere and potentially affect life. For example, the flare from the boat GRB was so intense that it significantly affected Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash from the GRB released an enormous amount of energy, interacting with Earth's atmosphere and causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still studying. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so immense that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy 2.4 billion light-years away. This event only highlights the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. Additionally, studies of supernovae also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which has provided the foundation for understanding dark energy. Supernovae are a key focus for future astronomy. Their explosive nature and transformative impact continue to fascinate scientists and inspire new discoveries. While some are eagerly awaiting Betelgeuse's potential explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope. These missions will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place within it. Surely, you've heard by now that black holes can be so massive they can outshine entire galaxies. But did you know that some of them are quite mobile, roaming the Milky Way like cosmic ghosts, undetectable? You might be surprised to learn that the nearest black hole to Earth is closer than you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints, frequencies that may hold the key to unlocking the deepest mysteries of the universe. However, these waves interact in a far more complex way than previously imagined. Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. While we are familiar with small black holes, the remnants of dying stars, and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. Recently, the Hubble Space Telescope, our eye in the sky, focused on Messier 4, the star cluster closest to Earth. What it discovered was groundbreaking: a black hole with a mass about 800 times that of our Sun. This celestial object is located somewhere between 6,000 and 7,200 light-years away from us. Why is this discovery so important? For years, astronomers have struggled with a gap in the black hole genealogical tree. We had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But intermediate mass black holes have been the missing link, mysterious relatives everyone has heard of, but no one has encountered. An equally interesting question is how these intermediate mass black holes form. One theory suggests they could be the nuclei of dwarf galaxies that lost their outer stars when they merged with larger galaxies. Another theory proposes they may have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, played a key role in this discovery. The presence of a black hole affects its cosmic environment, and by studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may play key roles in the formation of galaxies and hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,857 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light-years from Earth. But what does this proximity mean in the context of black holes, and why is it important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would have made it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it is a binary star system where one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened new possibilities for studying stellar evolution and interactions. After HR 6819 was disqualified, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. Gaia's primary task is to map the Milky Way in unprecedented detail, and thanks to this meticulous work, Gaia BH1 was discovered as the closest known black hole to Earth. Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as their mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle, and the closer a black hole is, the more accurately these instruments can measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public's imagination. It makes the cosmic seem more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to engage with astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or binary star systems. But what happens when a black hole roams the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue, and how do astronomers even find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first-ever unambiguous discovery of a wandering black hole located 5,000 light-years from Earth. This black hole has a mass 7.1 times that of our Sun and moves at a staggering speed of about 28 miles per second. The key to this groundbreaking discovery lies in a phenomenon predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the star's light. This creates a brief brightening phenomenon, which is how this wandering black hole was detected. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. This is likely how our newly discovered wandering black hole began its cosmic odyssey. What's even more intriguing is the speed at which this wandering black hole is traveling, about 28 miles per second, which is quite fast compared to nearby stars. This speed is likely the result of the impact of a dying massive star, sending the black hole on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia Telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more of these space travelers. These future discoveries will not only increase the number of known rogue black holes but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled by the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into young, gas-rich galaxies, the cradles of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful radiation. This heated gas is less likely to fall into the black hole, creating a feedback loop that stabilizes its size. However, as the galaxy grows, more gas is pushed toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows more slowly. If it's too small, it catches up due to the abundance of gas and dust in the galaxy. Some galaxies, however, defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, star formation ceases, and they turn into red nuggets, still retaining their enormous black holes. As we move deeper into the black hole abyss, it becomes clear that young, gas-rich galaxies serve as the birthplace of various black hole phenomena. Whether they are luminous black holes, intermediate mass wandering black holes hurtling through space, or the nearest black holes to Earth, their origins can often be traced back to these bright, young galaxies. Understanding the cradles of these cosmic giants helps unlock the mysteries that black holes hold. Now, let's look at something truly rare, the collision of black holes. When this happens, they create a cosmic symphony of gravitational waves that ripple through the very fabric of spacetime. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, testing our understanding of gravity and general relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects, presenting a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond, a linear model, the throw of a stone creates an isolated ripple. In a stormy sea, a nonlinear model, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies, or chirps. These sounds are like individual notes in a cosmic symphony, each telling us something about the properties of the colliding black holes. They offer a new way to test the limits of general relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process mirrors the larger universe, where galaxies and their central black holes grow together. Colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merged to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we delve deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. Each discovery, from the frequencies they generate to the nature of gravity itself, will undoubtedly add new layers to our understanding of the universe. As our telescopic technology becomes sharper and computational models more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal. One of the most interesting mysteries in our universe, generated by the equations of Einstein's general theory of relativity, is the theoretical counterpart to the black hole, the white hole. Imagine a region of space where, unlike the all-consuming black hole, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by ejecting matter and energy, glowing violently against the dark canvas of space. In a universe governed by the concept of time zero, where events flow from past to future, a white hole presents a tantalizing paradox. It's like watching a space movie in reverse, where the rules of gravity and time seem to be rewritten. But are these celestial wonders merely mathematical curiosities, or could they hold the key to understanding deeper truths about our universe? Let's explore the mysteries of white holes, examining their theoretical underpinnings, enigmatic characteristics, and potential role in the grand history of the cosmos. In the early 20th century, Albert Einstein revolutionized our understanding of the universe by developing the general theory of relativity. This groundbreaking theory proposed a radical idea: gravity is not a force pulling objects together, but rather a curvature of spacetime caused by mass and energy. Imagine spacetime as a fabric stretched like a cosmic trampoline. When an object with mass, such as a star or planet, lands on this fabric, it creates a dip. This curvature directs the motion of other objects, which move along curved trajectories in spacetime. This is how Einstein envisioned gravity. Einstein's theory led to the prediction of black holes, regions in space where the gravitational pull is so strong that nothing, not even light, can escape. These cosmic giants form when massive stars collapse under their own gravity, distorting spacetime to an extreme degree. Enter Karl Schwarzschild, a brilliant physicist who, while fighting in World War I, discovered an interesting solution to Einstein's equations. Schwarzschild's solution described spacetime around a spherical, non-rotating mass, such as a star. His work laid the foundation for understanding black holes, but it also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its polar opposite exist, a region where nothing can enter, but only leave? This led to the concept of a white hole. Just as a black hole represents the endpoint of gravitational collapse, a white hole can be thought of as a reverse black hole, a cosmic fountain ejecting matter and energy. However, unlike black holes, which have been observed, white holes remain a theoretical concept, a tantalizing possibility in the vast cosmic mystery. In astrophysics, the path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the same complex equations of the general theory of relativity that predict black holes. The math behind white holes is solid, but it's like a puzzle missing key pieces. We understand their theoretical foundation, but the real challenge is to connect these mathematical models to observable phenomena. Imagine a universe where, instead of collapsing inward, a region of spacetime does the opposite. It explosively ejects matter and energy. This is the essence of a white hole, a mirror image of a black hole where the flow of time and matter is reversed. But can these mathematical concepts exist in our physical reality? Scientists continue to debate this complex issue. Some theorists suggest that white holes might be remnants of the early universe, exotic structures woven into the very fabric of spacetime. Others propose that they could be the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed by the black hole. Quantum gravity presents a new idea, suggesting that when a black hole evaporates over many epochs and loses mass, it might eventually reach a point where it can no longer sustain itself and transforms into a white hole, releasing its trapped contents back into the universe. However, there are significant issues with the physical existence of white holes. The laws of thermodynamics, particularly the concept of entropy, present a major challenge. Entropy, a measure of disorder, increases throughout the universe. Yet, white holes, by nature, decrease entropy, contradicting this fundamental principle. Moreover, the stability of white holes is controversial. Some theories suggest that if they did form, they would be extremely unstable and likely collapse almost instantaneously into black holes. In outer space, white holes are one of the most enigmatic and paradoxical concepts. These mirror images of black holes challenge our traditional understanding of physics. To delve deeper into white holes, we must first understand their defining feature, the event horizon. Unlike black holes, where the event horizon marks the point of no escape, a white hole's event horizon marks the boundary of impenetrability, where matter and energy are ejected in a cosmic spectacle. White holes are also fascinating due to their association with time reversal. In our universe, time generally flows in one direction, from the past to the future. However, white holes appear to reverse this flow, like watching a space movie played backward, where time and space follow reversed rules. This brings us into a realm filled with paradoxes and challenges. One of the most important paradoxes is related to entropy. According to the second law of thermodynamics, entropy should always increase in a closed system. But white holes appear to violate this law by ejecting matter in a more ordered state. This presents a major problem for our understanding of physical processes in the universe. How could a white hole exist if it contradicts such a basic principle? Another paradox involves the arrow of time, which normally moves steadily forward. White holes suggest a scenario in which time could flow backward, at least from a certain perspective. This idea challenges not only our understanding of time but also the very nature of causality in the universe. To summarize, white holes are characterized by their event horizons, their expulsion of matter, and the concept of time reversal. While they present an intriguing and paradoxical picture, white holes remain in the realm of theoretical physics for now. As we continue exploring the mysteries of the cosmos, white holes push us to rethink our understanding of the universe. These theoretical objects may not just be anomalies, they could have profound cosmological implications. Consider the Big Bang, the massive explosion that marked the beginning of our universe. Some theorists suggest that this pivotal moment was not a random explosion but rather the result of a white hole of unimaginable size, a burst of matter and energy that created the cosmos. This perspective offers a radical new interpretation of the origin of our universe, hinting that white holes may play a role in cosmic genesis. Imagine a white hole not as just a theoretical idea, but as the very source of the universe's creation. In this scenario, could be envisioned as a white hole of unimaginable scale, spewing out matter, energy, and spacetime, which eventually evolved into the stars, galaxies, and planets we observe today. This view offers a radical rethinking of the Big Bang. Instead of an undefined singularity, we have a white hole, an entity defined by the laws of physics, although in a form that stretches our understanding to its limits. This white hole might have been the initial spark that set the stage for subsequent cosmic evolution. If the Big Bang was indeed a white hole, it raises profound questions about the nature of our universe. What was the source of this white hole? Was it the result of the collapse of a universe from another dimension or a process beyond our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline, where the beginning and end of cosmic events are intertwined in ways we have yet to understand. This idea of the Big Bang as a white hole organically links with the Big Bounce theory, which suggests that the beginning of our universe could be the result of the collapse of a previous universe. It unites the concept of cyclical universes, proposing that every cosmic end could give rise to a new beginning, similar to the explosive genesis of a white hole. The existence of white holes may also support the concept of parallel universes. If white holes can eject matter and energy, could they be gateways to other universes? This possibility is connected to the multiverse theory, which postulates the existence of multiple, possibly infinite, universes parallel to our own. In these parallel universes, there may be different laws of physics, alternate histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in spacetime. Theoretical models suggest that wormholes could link distant regions of space, and possibly even different universes. If white holes are linked to wormholes, they could serve as cosmic portals, opening pathways to remote parts of the universe or entirely different dimensions. This connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel over vast cosmic distances or even between different universes? Looking into the future of astrophysics, we see a lot of scientific research currently touching on the subject of white holes. However, two research papers stand out, shedding light on the mysterious nature of these cosmic objects and offering new ideas that could revolutionize our understanding of white holes. The first paper takes us to the very edge of black and white holes, exploring their close connections and focusing on the physics occurring near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. They differ from standard curvature coordinates in the near-horizon region to emphasize the distinction between black and white horizons, which depends on near-horizon physics. This study suggests that black holes may not be the cosmic dead ends we once thought. Instead, they might exist in quantum superposition with white holes, creating a scenario in which observed phenomena could hint at the existence of these theoretical white counterparts. The paper also discusses the role of quantum physics in these near-horizon regions, suggesting that quantum effects could dominate, leading to significant implications for our understanding of white holes. However, the authors emphasize a problem in observational astrophysics. While there is substantial observational evidence for black holes, support for the existence of white holes remains relatively weak. Moving on to the second paper, titled New Black to White Hole Solutions with Improved Geometry and Energy Conditions, the focus shifts to how black holes might convert into white holes, guided by the principles of quantum gravity. It presents models where the effects of quantum gravity prevent the formation of singularities inside black holes, providing a smooth transition into white holes. This approach solves the long-standing paradox of information loss by assuming that matter can pass through a black hole and emerge in a white hole. The paper also examines geodesics within these models, confirming the completeness of particle trajectories during the transition from the black hole region to the white hole region. This supports the idea of a continuous, unimpeded flow of matter, reshaping our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we stand on the brink of a new era in astrophysics. The future of white hole research promises to unveil new aspects of the universe, where the boundaries between quantum mechanics and general relativity begin to blur. To summarize, the future of white hole research appears promising. Who knows? Perhaps we will soon discover indirect evidence for the existence of these intriguing objects. There is a hidden order in the void of space, a subtle force that governs the movements of celestial bodies with an invisible hand. Far from the chaotic randomness one might expect in the vast cosmos, there exists a mysterious harmony, a set of invisible rules that dictates the paths of planets, moons, and asteroids with remarkable precision. Consider that the giants of our solar system are not merely isolated spheres of rock and gas but participants in a grand gravitational dance, each move influenced by the forces generated by their cosmic neighbors. Among these actors are Jupiter and its moons, with the asteroid belt, a vast ring of debris, behind them. This belt contains voids of mysterious origin, hinting at an unseen force silently shaping its structure. Even distant Neptune and Pluto tell a story of complex gravitational interactions, locked in such a precise rhythm that their orbits never intersect. These patterns and rhythms emerge constantly in the vastness of space, hinting at the underlying order governing the universe. Orbital resonance is the concept behind this behavior, a mechanism that is both simple and bewilderingly complex at the same time. Let's explore it further. Behind the night sky's facade, a complex network of forces dictates the movements of celestial bodies. Gravity, the fundamental force that keeps us grounded on Earth, extends far beyond our planet, creating the architecture of the cosmos on a grand scale. At the center of our solar system is the Sun, a colossal nuclear furnace whose gravitational pull commands the motions of the planets around it. This gravitational interaction is not one-sided. Each planet, in turn, exerts its own gravitational influence, creating a complex network of forces that shape their orbits. When two celestial bodies come close together, their gravitational fields interact, influencing one another in a cosmic tug-of-war. This interaction can lead to subtle changes in their trajectories, a phenomenon most pronounced in systems with closely rotating bodies, such as Jupiter and its Galilean moons. Take Jupiter, for example, the giant of the solar system, whose massive gravitational field holds a retinue of moons. Among them, the Galilean moons, Io, Europa, and Ganymede, exhibit a remarkable phenomenon known as mean motion resonance. This occurs when the periods of their orbits around Jupiter maintain a constant ratio, a delicate balance that prevents their trajectories from becoming chaotic despite their close proximity. This gravitational interaction leads to a rhythmic alignment of the moons, ensuring their long-term stability. The forces at play don't merely pull the moons along their trajectories but also push them into positions that minimize potential disruptions to their orbits. Beyond the region of Jupiter and its moons, the gravitational interaction extends to the asteroid belt and beyond, where countless rocky bodies are influenced by the gravitational pull of nearby planets. This interaction can create gaps in the asteroid belt, regions devoid of asteroids, formed by the resonant effects of Jupiter's gravity. Based on this, we can conclude that gravity acts as a cosmic weaver. Its threads pull and shape the trajectories of celestial bodies, creating a harmonious order from potential chaos. This gravitational influence, a fundamental aspect of the universe, provides the basis for the interaction of planets, moons, and stars. But is it as simple to understand as it seems? In the gravitational embrace of Jupiter, the largest planet in our solar system, lies a remarkable example of cosmic harmony, the Laplace resonance. This unique gravitational relationship involves the three major moons of Jupiter, Io, Europa, and Ganymede, each a fascinating world, engaged in a synchronous orbital interaction that has intrigued scientists for centuries. Laplace resonance is characterized by the exact ratio of the orbital periods of these moons. For every 4 orbits that Io completes, Europa orbits twice, and Ganymede completes 1 orbit. Due to this gravitational pattern, the moons align at regular intervals in a cycle that repeats every 7 Earth days. Resonance is not just a curious phenomenon, it has profound implications for the moons themselves. Gravitational interactions, especially between Io and Europa, cause significant tidal heating on Io, fueling its volcanic activity. This energy dissipation also affects Europa, potentially contributing to the maintenance of its subsurface ocean. Laplace resonance provides a clear example of how celestial bodies, through mutual gravitational influence, can establish stable and predictable patterns that last for centuries. Though small compared to the gas giant it orbits, Mimas exerts a significant periodic gravitational influence on the particles within the rings. This effect isn't random, it occurs at specific points in the particles' orbits, as their orbital periods are in resonance with Mimas's orbit. For every 2 orbits that Mimas completes, the particles at the edge of the ring complete 1, creating a 2:1 resonance. This leads to repeated gravitational interactions at the same points in the particles' orbits. These repeated interactions accumulate over time, acting like a cosmic broom that clears the way, forming the Cassini division. The particles that once filled the space were either pushed into new orbits or clumped together to form larger bodies, leaving behind the void that marks the boundary between Saturn's A and B rings. This process is similar to nudging a seesaw at just the right moments. Each nudge adds a bit more energy to the system. In the case of the planet's rings, each gravitational push from Mimas shifts the particles, clearing a path. However, Mimas's influence and orbital resonance aren't limited to the Cassini division. Similar resonances caused by Saturn's other moons shape the complex structures of the rings, creating patterns of discontinuities and dense bands, making the planet's rings dynamic and ever-changing. Between the orbits of Mars and Jupiter lies the asteroid belt, a massive cluster of rocky remnants from the solar system's formation. However, this region is unevenly filled, with distinct gaps known as Kirkwood gaps. These gaps aren't the result of missing asteroids but instead reflect regions where Jupiter's gravitational influence has swept through, clearing out material. Kirkwood gaps are named after Daniel Kirkwood, who, in the 19th century, observed that these gaps correspond to orbital resonances with Jupiter. In these resonances, the orbital period of an asteroid in the gap is in a simple ratio with Jupiter's orbital period, such as 1:2, 2:3, or 3:4. At such distances from the Sun, an asteroid's orbit periodically aligns with Jupiter in a pattern that repeats each time it completes an orbit. Over time, these repeated alignments expose the asteroid to regular gravitational jolts from Jupiter, altering its orbit. When an asteroid falls into one of these resonant gaps, repeated gravitational pulls from Jupiter can increase its orbit's eccentricity, shifting it to a more elliptical trajectory and pushing it out of the resonance gap into a different orbit. To visualize this phenomenon, imagine an asteroid approaching one of these resonant orbits. As it nears, Jupiter's gravitational pull synchronizes with the asteroid's orbit. If this synchronization falls within the Kirkwood gap, the asteroid experiences repeated gravitational pulls that shift its orbit slightly each time it completes a loop around the Sun. Eventually, these pulls alter its orbit, moving it out of the resonance gap and into a less perturbed region, where Jupiter's influence is less synchronized. In the outer part of our solar system, beyond the gas giants and the icy Kuiper belt, lies another fascinating story of celestial harmony. Neptune, the eighth planet from the Sun, and Pluto, a dwarf planet that was once considered the ninth, share a unique gravitational relationship that prevents them from colliding. This relationship is governed by a 3:2 resonance, a gravitational lock that ensures that for every 3 revolutions Neptune makes around the Sun, Pluto completes 2. This rhythmic interaction is not just a coincidence. The resonance has a profound influence, shaping their orbital paths so that despite their overlapping orbits, Neptune and Pluto never collide. Pluto's orbit, heavily influenced by this resonance, is noticeably eccentric and tilted, looping above and below the plane of the solar system. Over millennia, this harmonious arrangement maintains balance, highlighting the complex laws of physics that ensure stability and order in the vastness of space. But what do all these phenomena have in common? The moons, planets, their rings, and asteroid belts. Why are only some of them affected by orbital resonance? The answer lies in the subtle interplay of celestial mechanics, where eccentricity, inclination, and gravitational forces come together. Orbital resonance is based on 3 key factors: eccentricity, which measures the elongation of an orbit; inclination, the tilt of an orbit relative to a reference plane, whether it concerns a star or another celestial body; and gravitational forces, which tie everything together. These elements are intertwined, determining whether a body falls into the grip of orbital resonance or avoids it. When a celestial body enters resonance, its orbit becomes locked in a gravitational interaction with another, usually much larger, body. This lock can increase stability, as seen with Neptune and Pluto. However, there are exceptions where objects are ejected from their trajectories, creating gaps in regions such as the asteroid belt. The role of eccentricity and tilt in this process is significant. A small increase in eccentricity, for example, can dramatically alter the gravitational interaction of a body, bringing it into or out of resonance. Similarly, inclination can tilt an orbit so that it interacts with the gravitational influence of another body at just the right point to enter resonance. This complex balance of forces makes orbital resonance a selective phenomenon, affecting only those bodies that meet the precise conditions necessary to synchronize with the rhythm of their larger neighbors. It's a cosmic lottery, where the prize is a stable orbit or, in some cases, total expulsion from the system. Looking beyond our solar system, we see how orbital resonance plays out on a grand cosmic scale, determining the fate of exoplanetary systems across the universe. These distant systems, with their unique clusters of planets, offer a fascinating glimpse into the complex design of the celestial mechanics that govern them. Observations of these distant worlds have revealed cases where planets keep pace with one another, their orbital periods maintaining an exact relationship. One striking example is the TRAPPIST-1 system, where several Earth-sized planets are locked in a complex chain of resonances. Such configurations raise intriguing questions about the formation and evolution of planetary systems, challenging and refining our theories. Meanwhile, the major planets of our own solar system do not show a clear pattern of orbital resonance with each other. Their orbital periods don't follow a simple integer ratio that would indicate resonance. While there are near resonances, such as the 5:2 resonance between Jupiter and Saturn, they are not as precise or stable as the resonances between moons or in more dynamically bound systems like Pluto and Neptune. The implications of these observations go far beyond merely cataloging celestial phenomena. They offer insights into the processes governing planet formation and suggest that resonances may play a key role in the assembly of planetary systems from protoplanetary disks orbiting young stars. As we continue to observe and study these phenomena, each new discovery reveals another layer of the intricate design of the universe, bringing us closer to understanding the fundamental principles that govern celestial motion and shedding light on the very essence of our existence.